These are your notes for section 5.7, graphing inequalities in the coordinate plane. Okay, basically today what we're going to be looking at is we're going to take that idea of graphing inequalities on a number line and we're going to expand it to involve the coordinate plane, your XY grid. Okay, we're only going to be dealing with two variables today. This should be review. There are lots of applications in the business world when you're looking at costs and production and things like that. They really look at inequalities in those situations. So that's what we're going to be looking at today. And like I said, I think this will be a pretty easy section for you because we have done this before. Okay, this is interesting to me when we talk about this idea of a boundary line and its cutting of a plane. Remember when you're talking about a plane from geometry, you're thinking about like your desktop. Expand that desktop to be the largest desktop you can ever imagine. It goes on forever in all directions, which means you obviously can't sit on the desk because it's going forever, so you can never get to that side where you can get under it. But it keeps going forever and ever, and it cuts into hills and whatnot. If I have an XY grid, and that is representing my giant desktop. Okay, oh, my arrows are kind of off here. I can put a line on it, and this could be my boundary line here. Now, once I draw that boundary line, it is cutting that desktop into two pieces. We call them half plane and a half plane. Now, it doesn't necessarily mean that those two planes are equal, and that's kind of confusing to kids because they'll say, well, this bottom half plane is going to be bigger than the top half plane. Well, you got to realize that we're dealing with the concept of infinity where things are going forever in the right and forever to the left. So when you say one side is bigger because it includes sections here of quadrant 2 and like more of quadrant 1 than the other half plane, that really isn't going to be relevant because really the XY grid, what that does, it just kind of marks off locations. It's kind of like a convenience for mathematicians to use so we can refer to certain points. It doesn't necessarily have to do with the whole size of a plane because that plane is infinitely large. It keeps going forever. But when we have a boundary line, we call it a half plane and a half plane that it separates. It does not have to be solid. We are allowed to make it a dashed line, kind of like an asymptote, if you're just dealing with greater than or less than, but it will be solid if you're dealing with the equal to sign. So that's the idea of half planes. Shading. You have done this before, like I said. You shade the part of the graph where the solution set. So if I'm dealing with y is greater than 2x plus 1, okay, I'm going to have a y-intercept of 1, so I'm going to go up 1. My slope is 2, so I'm going to rise 2, run 1. I could do that forever. I'm going to go the opposite direction though so that I can have space here, down 2, left 1. This is going to be a dashed line because it doesn't equal 2x plus 1. So it's going to be greater than. The boundary line though is the same as if I took out that greater than sign and replaced it with an equal sign. Because it is a greater than sign, I'm talking about where are values bigger than this boundary line. Greater, bigger, and we are talking about the area above. Okay? What this is telling me is that all of these points in here make this equation true. So let's pick a point, like let's say 0, 10. That's definitely going to be in that shaded region. I could tell by my graph. If I plug that in, I will get 10 is greater than 2 times 0 plus 1. 10 is definitely bigger than 1, so you can see that's true. There are so many points that make that true, infinitely many. There are also infinitely many points that will make that statement false. For example, 0, 0 is definitely not in my solution set, and I could see that algebraically as well, because 0 is not bigger than 2 times 0 plus 1, because last I checked, 0 is not bigger than 1. So if it's not in the shaded region, it makes it false. If it is in the shaded region, it makes it true. If it's on the asymptote line, it's going to also be false because it says greater, not greater than or equal to. You do not need to use your graphing calculator on this activity. You can just use the rules you know. You can. I just feel like it's kind of a waste of time. Greater is going to be dashed, and we're going to shade above. Less than is going to be dashed, shade below. Some people might like if I put an E there. And if I add the equal sign, then it won't be dashed, then it'll be a solid once you add those in there. I'm having all sorts of spelling problems. Pretend I'm not. Okay, so let's move on here. How do you know if it is a solution? You can plug in the ordered pair to check. For example, right here, y is less than negative 1/2 x plus 2. Again, I go up to where my y-intercept would be. Slope is -1/2, down 1 over 2, down 1 over 2. This case, we're dealing with a dashed line. Shade below, we're looking at down here. Okay, -4, 5, -4, 5. That would be here. It'd be kind of hard to tell if it's in the shaded region, so I should go ahead and check it algebraically. 5 less than -1/2 times -4 plus 2. If 5 less than 2 plus 2, no. 5 is not less than 4. That is not a solution. So that will be in the unshaded region, non-shaded region, I don't know, whatever you want to say. Let's look at this. Is a set of points satisfying this inequality above or below this boundary line? The boundary line is definitely right. We're curious about which way we're going to shade. I will tell you, some kids can just tell by looking at it. I still like to get y by itself because sometimes with inequalities, that sign gets flipped when you're going into slope-intercept form. So I do go ahead and get y by itself, and that allows me to tell whether or not that sign flipped, and it did not flip in this case, but there will be some examples where it does. Okay, so you do need to be careful. This is less than, it's going to be below because it's lower, less than, it will be below the boundary line. But like I said, if this was a minus sign, it would be above because when we got y by itself, that inequality sign would flip. So be very careful on these types of examples. Lattice points. Okay, do you know what this word lattice means? Okay, I'm going to stereotype some grandmas here. I used to always, when I think of lattice, think of my grandma's porch. So she has this porch. Kind of like, this is really bad drawing. Okay, and then underneath the porch, she had, this is called lattice. Or lattice work, maybe. And I always thought that cats lived under there, which is beyond the point. But I would never go under there because I was afraid of cat and cat pee. Okay, so there's that wood, it's like wooden, like crossing like that. Other times people have it like in their gardens, like ivy can grow up it. That's what the word lattice comes from, I think. Well, sometimes, like going back to that example that I erased it. Oh, no, I didn't. Here it is. Sometimes you're dealing with situations where you're talking about numbers of items, and then the domain and range can't be all real numbers. It has to be like integers. So if that's the case, then I shouldn't technically solid shade this because that's saying all those points in between there. Instead, I would put dots, okay, because those are the only number of combinations. It would look kind of like this. So you have these dots representing things, okay? This happens a lot in real world because you're talking about production or hours. Hours you can probably have a half, but if you're talking about people, then definitely you're not going to have a half a person. If your graph looks like that, we call it lattice points. Here's my advice to you. I never graph lattice points. It's a kind of tedious. I go ahead and shade it. So if I was to graph this, I wouldn't have put the dots. I would have just shaded it like normal. Then when I'm asked the question, how many people or whatever, I say, oh wait, can't have half a person. I need to remember that these only work for integers. Okay. I am reflective when I answer my questions and not when I'm graphing. Now, I've seen some of your work. Some of you do make silly mistakes and you're not reflective. Does my answer make sense? If that is you, you might want to take the time and put in those lattice points, or at least on a few of them, so that you're reminded, oh, this doesn't work for everything. It just works for whole numbers or integers or whatever you're dealing with. Okay, pumpkin pie anyone? We will end it there, and I will talk to you tomorrow.